Hello everyone, Dr. Tullis here, continuing our lessons in the electrochemistry unit with a clear focus today on voltaic cells, called galvanic cells as well. Either word or either vocabulary term can be used. To talk about common batteries, we'll begin by describing the function of a galvanic cell and its components, and we'll work towards writing out cell notations that symbolize the composition and the construction of these galvanic cells. First, I want you to consider this redox reaction. We have a single replacement reaction. And we said that single replacement reaction falls under that umbrella, where we can also call it a redox reaction. And in this reaction that we've got going on, we've seen this before, we have a copper wire, so solid copper, Cu, reacting with an aqueous solution of silver nitrate, so that's our AgNO3. So we have copper wire, this is my copper wire, and the solution right here is our silver nitrate. And this is a single replacement, like we said. So we have a metal added to a compound, and that's going to, if this copper is active enough, to kick out that silver from the silver nitrate. So that silver is then by itself, and we can see right here that we've got silver by itself. And then that copper takes the place of silver. So I have copper nitrate. So that copper goes into the solution, becomes part of that compound, and I have solid silver left behind. And we can see here that as time goes by, the silver metal is going into solution, and you can see this silver starting to plate out the original copper, so much so that the copper now in solution, that copper ion is a blue color. Notice how that solution is blue. What's plating out is a solid silver coating itself on that original copper spring. And so this single replacement reaction, like I said, is also known as a redox reaction. We can eliminate the spectator nitrate, and that leaves us with a net reaction of our solid copper plus our 2Ag, that makes that Ag plus, and then 2Ag elemental silver plus copper 2 plus. Now, if we wanted to find the oxidation half reaction, I'm going to change this color. Here, if I look at copper, we know everything in elemental state has the oxidation state of 0. So silver over on the right is also. And then we also know the oxidation state of our ions are given. So look at copper went from 0 to +2. That is our Leo. Leo the lion, losing electrons. We went from 0 to a positive charge, so we lost electrons. That's oxidized. So I could write that as our Cu to Cu plus 2. When I balance this out, again, this is 0 on the left, and this is +2. So on the right, I need to add 2 electrons. Again, we know that our oxidation, if we're losing electrons and it's being oxidized, then my electrons are in the product. Let's look at our reduction. That means that our silver, here's our silver. We went from a +1 to a 0. This is our Gur. So our reduction half reaction is going from 2Ag plus, and on the right, 2Ag solid, our elemental form, And again, I'm going from +1 and 0. To get my left side to be 0, I need to add 2 electrons. 2 negatives and 2 positives equals 0, same as my right side. Again, this is I gained electrons, therefore it's in the reactants. We can also look at this and know that because I lost 2 electrons in my oxidation, I needed to gain 2 electrons in my reduction. This is a review of our oxidation-reduction reactions. So hopefully you feel comfortable with this. We've been doing a ton of practice with that. But in the next step, when we think about doing useful work with a redox reaction and actually generating electricity, generating a voltage that we can capture and perform work with, we end up separating the two half reactions, physically separating them into separate containers and preventing them from even coming into contact. So consider this same reaction, but one that uses a device to prevent that physical contact between the reactants and the transfer of electrons between the two halves that is occurring between a wire and external circuit that contacts the separated reactants. So let's look at this very carefully. So let's go through and draw this together, what we've got here. In 1/2 reaction, which is just a beaker filled with solution and an electrode placed in it, an electrode will either be a cathode or an anode depending upon the reaction. In this particular picture, this is pure copper metal. Now, in the last picture, it was a wire of copper coiled in a spring, but here generally an electrode is just a flat piece of metal. And in the solution, we have, a copper nitrate solution. And we'll write that down here. Our solution is 1 molar of copper nitrate, copper 2 nitrate, so CuNO3 2. Now, usually in the lab, you'll have a little alligator clip here to clip to this metal, and then that will be connected, the alligator clip will be connected to a wire, and then the wire is connected to a voltmeter. So you can read the voltage here in this battery. And then it continues on into this next half cell. And again, this is just another beaker. This beaker contains an electrode made of pure silver. So this is just a piece of silver metal, and in solution, we have our silver ion, which is just Ag+, because that is a standard solution, 1 molar. 1 molar is standard concentration of silver nitrate, so AgNO3. Now let's think about what's happening in this cell. In the copper side, let's go back here to our previous one. We said right here that copper was going through oxidation and that our solid copper was generating copper 2 ions and electrons. So let's write down what's happening here underneath. We've got copper generating copper ions and 2 electrons. Let's look at the other side. What's happening over there? We've got a reduction happening. So we have our Ag+, we've got our reduction happening. So actually I'm going to write oxidation. Over here we have our reduction, where we have our Ag+, plus electrons to give me Ag solid. Now, if I look at this reaction, see here, I'm generating 2 electrons. And over on the right side, I need 2 electrons. So we actually have right here, the electrons produced are going to travel through this voltage meter into my other half reaction. The 2 electrons are going to flow across that wire. Now, right now we have an incomplete circuit. The voltmeter would read 0 because the flow doesn't have a complete circuit. Now, as I just said, we've got flow of electrons through this current. So they're moving through this current by a potential difference, and they're entering into this half cell on the right. But again, the circuit is incomplete. I have to complete this circuit, and to do that, I have to allow ions to move past from one back to the other. So this is called our salt bridge. Now in the lab, I often just use a salt-soaked filter paper, a piece of filter paper that's been soaking in salt water to just lay across one beaker to the other. So that makes a great salt bridge, something that is, there's a hollow tube in this picture on the left, packed full of sodium nitrate, which is a salt. The salt bridge serves a very important purpose that we're going to look at further in just a moment. But as I try to draw on this screen, I wanted to go through some of these highlights of this battery, this galvanic cell. Now let's pick up some further vocabulary. We drew on the left side the oxidation reaction. Oxidation always occurs in the anode half cell on the anode. And on the right side, we drew reduction. And you should know that the cathode is the half cell where reduction occurs. And in notation, we always write the anode on the left and the cathode on the right for voltaic cells. And this is for voltaic or galvanic cells. Now, I'm emphasizing that voltaic and galvanic cells are the same thing. Galvanic cell is an honorary name named after a scientist, Galvani, and a voltaic cell simply comes from the voltage, the unit that we measure potential difference in. But do hear those as the same term. And at the end of this chapter, when we flip directions for non-spontaneous reactions with electrolytic cells, this whole thing flips around and the cathode will be on the left and the anode will be on the right. But we're not there yet. For standard notation on a voltaic or galvanic cell, cathode is on the right and anode is on the left by standard conditions. And so flipping back to this one that's nice and neat and pretty, here I have this external circuit. The electrons are being generated in the oxidation half cell, which is on the left here, right? This is our oxidation. This is our reduction. And so we see the current beginning to flow. Remember, in our oxidation down here, our oxidation, it's generating electrons. So the generated electrons, the current begins to flow. And it's flowing from the anode into the cathode. And it's going in that particular direction. So this is the electron flow, kind of in a clockwise fashion from anode to cathode. Okay, that needs to be in your brain. So think of the chemistry that's happening here. We said in the anode half reaction, aqueous copper ions are being formed. Right? So I'm flipping back here. We said aqueous copper ions are being formed. So over time, this copper, this plate of copper, I'm going to flip back here again, is actually losing mass. This plate of copper is turning into aqueous ions of copper. And so we can see this solid copper is dissolving into the water. It's becoming copper +2 ions. Now, as we generate more and more copper +2 ions, we have to keep the charge balanced, and that's the job of the salt bridge. Now, the salt inside of this packed piece of glass tubing, the sodium nitrate, is made of two different ions. We have our Na plus ions and our NO3 minus ions. Right? So if we look at this salt bridge, which is NaNO3, we can see the ions that make up NaNO3. We have Na plus and we have NO3 minus. Now, if the anode, the left side, the oxidation half cell, is generating more positive charge as time goes by, so as that electrode is going from solid copper to aqueous copper ions, we have to neutralize those positive charges. And that's where that nitrate is coming from. It's coming from the salt bridge. This NO3, because we're taking our solid copper, and we know oxidation is happening. That solid copper is turning into copper +2 ions. And there's more and more and more and more of it. So this NO3 minus from the salt bridge is coming in to neutralize that. So the nitrate is going right into solution to balance the positive charge that's being generated, which is then keeping it electrically neutral. So now let's turn our attention over to the right side, the cathode, which is our site where reduction is occurring. And we know that electrons are being gained. Notice that the electrons are coming into solution. We can see that. Remember, we've got from our anode, we have electrons flowing out of our anode. We can see our flow of electrons here in this external circuit. And the electrons are flowing into solution. Therefore, they're being gained. But in terms of the chemistry, the solid silver is actually having more mass added to it as time goes by, because the aqueous ions of silver are plating onto that silver electrode. So the left side, this copper is actually losing mass, and my right side, my cathode, is gaining mass over time. So on the left here, this copper anode is losing mass over time. That copper is degrading into those copper +2 ions. And then on the right side, my silver cathode is gaining mass as the aqueous ions plate onto that silver cathode and just kind of add mass as pure silver. So if we're removing these positive ions on the right here, the cathode, and plating it onto that silver, that means I'm left with an abundance of the nitrate ions. And that's where the chemistry comes into play, where we have to balance that charge. So that is the job of the sodium from the salt bridge. The sodium's coming in. So for every one silver ion that's plating onto the electrode, we have to balance that missing charge. And the sodium will migrate into the solution to keep an electrically neutral charge overall. So because we add copper ions in oxidation, that nitrate comes down to neutralize the flow of anions from the salt bridges toward the anode. On this side, we see that electrons are being gained. The silver ion is plating out, therefore we balance the charge with the cations flowing into solution from the salt bridge. The cations migrate towards the cathode. And all of that is done to keep that electrically neutral overall charge. So we've just drawn out our first simple battery, haven't we? We've introduced terms such as anode, cathode, salt bridge, voltage, all kinds of good stuff. So let's look at this next picture here with everything rewritten on it, so you can compare your notes from the handwritten sloppy previous slide. So let's emphasize some points that we've discussed. You know, this picture is called a galvanic cell. A galvanic cell is composed of two half cells. Now remember, we separate the two half reactions. We have an anode side and a cathode side. We must complete the circuit to have electrons flow. We do that with some wires, so an external circuit. Typically, you're going to see a pair of alligator clips, like in the lab, and to create our simple circuit, we'll use our alligator clips and some wires. On the left side, we always have the anode. And by convention, we'll always write the anode. We know that oxidation occurs on the left side, the anode. So by convention, I know I can walk around this battery and look at it from any angle, but when I'm drawing it, draw the anode on the left, which is our oxidation. So we talked about the copper ion entering the solution from the metal. It goes from solid aqueous copper. And that makes sense because it's oxidation. Copper must be losing electrons to generate an electrical current. The flow of electrons is leaving the anode and going towards the cathode. The cathode, by convention, is always on the right. It's the site of reduction. Notice that the silver ion is coming out of solution and plating onto the silver electrode. Therefore, it's gaining mass. The silver is the cathode. To keep this electrically neutral, we see the positive ion migrating out of the salt bridge to balance the charge, so that as the silver leaves its ionic form, the sodium is coming in to attach with the nitrate. So remember, the site of reaction, really, where is the redox occurring? It's at the interface of the solution to the metal anode or the metal cathode. So it's the interface between the half reactions where we actually have redox occurring. To keep these reactants separate but maintaining the charge balance, the two half reactions have to be bound together by a tube or some sort of salt bridge that contains a positive ion and a negative ion to be able to migrate and keep those charges balanced as the electron circuit is completed. So it's usually either a tube filled with an inert electrolyte, such as sodium nitrate. I mentioned in the lab, it's very simple to do a salt-saturated piece of filter paper. Just soak a piece of filter paper or coffee filter, put it into salt water, get it wet, and it will complete a circuit just fine. So in this reaction, we've looked again, the same picture. Let's look at how we can take this complex picture and write about it in easy enough cell notation. So here are three kinds of components of what standard cell notation is telling you. It says that all relevant components of each half cell are represented by their chemical formulas, if they're compounds, or elemental symbols. All interfaces between component phases are represented by vertical parallel lines. If two or more components are present in the same phase, their formulas are separated by commas. And by convention, we write the anode on the left and proceed left to right, identifying the phases and interfaces encountered within the cell, ending with the cathode. And again, when we're writing our cathode and anode, a way to remember that, remember our anode is oxidation, and our cathode is reduction. One way that I use is anode starts with a vowel and oxidation starts with a vowel. And cathode starts with a consonant and reduction also starts with a consonant. Hopefully that helps you too. So let's look at what we have here. We are starting with our anode. And remember, our anode is going solid copper into solution, Cu2 plus 2 electrons. So we start off by writing our copper, solid copper. Oh, not S. And then there's the interface, right? Because we have our solid copper, and then this is the interface, that barrier. And we said it was going into solution. We know that Cu2 plus, this ion, is an aqueous ion, and our solution is that 1 molar copper nitrate. And then there's this double parallel line that represents our salt bridge. Okay, and then we proceed over to the right, which is our cathode. And remember, our cathode, our reduction site, we have silver ions, Ag plus. Remember, silver ions are in aqueous solution. Then going to silver solid silver. So we have to then next have our aqueous ions. We're just going in order here. Our 1 molar of AgNO3, and then our interface, right? So we're going AgNO3, and then finally ending with our Ag solid. So on our left here, we have our anode. On the right here, we have our cathode. We have our salt bridge right in the middle with our double parallel lines. And this is the standard cell notation for the battery that we have been drawing. Anode on the left, we use a parallel line to separate the phases that I find in there. And I want to emphasize, since anode is oxidation, copper metal going to copper ion, its oxidation order, we must show that oxidation. So we're going from 0 here to this +2. We have the salt bridge, the double line right here, and then we have the cathode, and we have reduction happening in the cathode. We have Ag plus 1 going to Ag0, which is a 0, elemental silver. So it matters the order in which you write it. We write the solutions and the solid on the left side. The solid comes first, and then the solution on the right. And then when we are going to the reduction, it's the solution and then the solid, because that is our changes. Our anode, our oxidation, we lose electrons, and our reduction, we gain electrons. I also want to emphasize that we do not balance the equation in the standard cell notation. In other words, I don't put the coefficients in there. There's no 2 in front of the silver, even though I know overall that reaction would need to be balanced with coefficients. But we do not include coefficients to balance equations in the standard cell notation. Okay, that is a lot to take in and digest. So let's do a practice. Let's take a look at what's going on in this picture. All right, first, on my left side, we know that we've got my anode. So we know that oxidation is happening on the left. And it looks like we've got a magnesium anode. So I have magnesium, a strip of magnesium that's all coiled up here. And it looks like I'm going from solid magnesium, again, oxidation. We know that I'm starting with that solid magnesium, 0 oxidation state. And it looks like it is going to solution, Mg2 plus. And electrons, we know that this is going to flow. The flow of electrons are going this way. So my electrons that it's releasing, I don't know, we're not balancing it right now, how many electrons, but the electrons that it's releasing is going to flow over to my cathode. So my cathode is over here. And we know that this is my reduction. And now what's happening over here? Actually, I'm backing up before we get into details about our cathode. We've got with our anode, where oxidation is happening, my magnesium is in a solution of magnesium chloride that it tells me down here. And I have this salt bridge, and my salt bridge contains sodium chloride, so regular table salt, giving me the sodium cations and chloride anions. And remember, we need that because when we have my solid magnesium here, it's going to turn into magnesium ions here in solution. And in order to keep it electrically balanced, these magnesium ions need the chloride ions to come into solution here to keep that balance. So now let's write down our cell notation for the anode. We have our magnesium in solid state, and that interface between the solid state and our 0.1 molar of magnesium chloride. That's aqueous. And then we have our salt bridge. Now we can go over, let's look at the cathode. Now, something unusual is happening over here from what we saw in the first example. Right here is the reduction half reaction. I'm changing an aqueous iron +3 into an aqueous iron +2. Now, how in the world am I supposed to hook an electrode, an alligator clip, to an ion that's in solution? And the answer is you really can't. So what we need to do physically is use an inert metal such as platinum or palladium or titanium. Of all the things I've just named, platinum and palladium are probably the least expensive. So we use an inert electrode and that's what this PT is. It's the element platinum on the periodic table. But it's not really part of the chemistry because it's inert. That metal, however, allows us to do what we have going on in the surface is coiled platinum wire reduction, and it's occurring at that site. So what we see, so it's happening at this site here. So what we see for the reduction half reaction, one electron is being gained and turning into the Fe+2. So how do we go about writing that? Well, remember in solution on the cathode side, we write the reductions first, because here, going back up here, my reduction, I need to have one electron to make that Fe3 plus convert into the Fe2 plus. Again, this is my reduction. So I need to show this at the bottom here. So I'm going to write down for my cathode side, I have 0.2, and here's my solutions. I've got 0.2 molar of iron 3 chloride, so FeCl3, and then we put a comma, and then we have 0.3 molar of FeCl2, so iron 2 chloride. These are both aqueous. Now these are both solutions. I can clearly see the reduction occurring. I went from a +3 to a +2. And this reduction is happening at the platinum inert electrode. So notice where my line comes in, separating the aqueous phase to the inert electrode, which is platinum in this case. And that's how I'll designate this cathode, which is our other half cell. So in solution, I've got my iron 3 chloride and my iron 2 chloride, and they're separated by that comma, all connected to an inert electrode called platinum. And like I said, platinum tends to be the most often used. It's easily purchased, and it comes in a nice coil just like copper does. So let's make sure that we see that. Oh, and I need to make sure that our platinum is solid here to complete our notation. So again, that platinum is our inert electrode. It is not the element that's being reduced. All right, now let's look at this more as a whole, looking at the two half reactions and then looking at a complete redox reaction and making sure that everything is balanced. So again, on my left, my anode, where oxidation is happening, I've got my magnesium solid, again, oxidation state of 0, and it's reacting to make our Mg plus 2 in aqueous solution, and 2 electrons. We need the 2 electrons because I've got a plus 2, and over here I need total net charge of 0. So I've got my Mg plus 2 and my 2 electrons. All right, then I also have my cathode, where reduction is happening, and that's where I've got my Fe plus 3 plus 1 electron to give me, and this Fe plus 3 is an aqueous solution, to give me my iron plus 2 aqueous solution. Again, we can make sure that everything is charge equal. I've got plus 3 and a -1, so that'll give me plus 2, and over here I just have plus 2. Now we know when I go to combine these, because on the left I've got 1 electron, on the right I have 2, that everything in my reduction half reaction we would need to multiply by 2. So let's look at our complete redox reaction. And I would bring this down and have my Mg solid plus 2 Fe 3 plus, that's in aqueous solution, reacting to form my Mg 2 plus in aqueous, and my 2 Fe 2 plus in aqueous solution. All right, let's make sure that everything is balanced. I've got 2 irons, 1 magnesium, 1 magnesium. Let's make sure that our charge is balanced. And I've got 2 3 pluses, so I've got plus 6 on the left. And I have 2 2 pluses, so that's 4 plus plus a 2 plus, so plus 6. So I'm balanced as far as atoms and charge. Also throwing out when we're looking at our reduction, when I have an aqueous, so my Fe3 plus, and over here I have my Fe2 plus, when I have two aqueous states, that's a clue that we're going to use an inert electrode There's no way that you can hook an alligator clip to complete a circuit with two aqueous solutions. So this is how you know you need an inert electrode involved to complete the circuit and give a site for the electron transfer. So that inert electrode most often will be written as platinum. Okay, great work. Let's keep processing some more examples. All right, let's see what we have here. A galvanic cell is fabricated by connecting two half cells with a salt bridge, one in which a chromium wire is immersed in 1 molar chromium 3 chloride solution. Another is copper wire immersed in 1 molar of copper 2 chloride. Assume the chromium wire functions as the anode. Okay, so write the schematic, which means just make the drawing for this cell. First, let's do that. So I've got my two beakers here, and we'll just do this for my beakers, and I've got my anode on the left, my cathode on the right. Hooked, we've got our alligator clips connecting both of our anode and cathode, and right here in the middle we've got our voltmeter, and we know that we have that salt bridge. Here we go. Now, let's change colors here. We know on the left is our anode. And it just told me that, what was my anode? The chromium. So here I've got Cr, chromium metal. This is my piece of metal that's hooked to my alligator clip. And then that also means that on my cathode side, I have my copper wire. So this guy here is Cu, copper. It also said that the solution, let's see, my chromium 3 chloride, this 1 molar of CrCl3. And over here with my copper, it's immersed in 1 molar of CuCl2, copper 2 chloride. Okay, remember our anode is oxidation. Cathode is reduction. All right, so let's write down what we know. We start with our anode, and we start with our chromium in solid form. And at the interface, we have chromium going to our 1 molar of chromium 3 chloride. That's aqueous. We have our salt bridge. And then we have reduction happening. My 1 molar of copper 2 chloride. And then there's the interface, copper in solid form. Now, let's make sure we know, again, we know that this is our anode. And we know the anode, there's oxidation happening. Solid chromium has an oxidation state of 0. And in this chromium 3 chloride, this is a +3. Going to 0 to +3, oxidation is happening. On my cathode side, copper is a +2 ion here, and copper in solid is a 0. We can clearly see that reduction is occurring there. The anode becomes more positive, right? As I lose electrons, I go from a 0 to a +3. It became more positive. The cathode is where reduction is happening. I become more negative. I went from a 0, or a +2 to a 0. I became more negative as I gained electrons. Another thing that I noticed was I don't need an inert electrode. In both of these, I've got solid chromium and solid copper taking place in that oxidation and that reduction. So I don't need an inert electrode. The copper and the chromium are solid chunks of metal, and they can be used as those own electrodes. All right, let's look at both of these half reactions. Well, let's look at my oxidation first. I've got my chromium, and it's going to be oxidized into chromium 3. Now, how do I know that it's chromium 3? Because when I'm looking at what was given to me, CrCl3, I'm just going to reverse crisscross. This 3 came from the chromium plus 3, and chlorine is minus 1. So I've got Cr3 plus, and because I have 0 oxidation state for elemental chromium, if I have a plus 3 on this side, that means that I also need 3 electrons on the right? So losing electrons is oxidation. So we've lost. We have 3 electrons on the right. Now this next one, let's do our reduction. We've got our copper. Again, how do we know that this is copper 2 plus? Because in CuCl2, reverse crisscross again, this copper is plus 2, chlorine's minus 1. So I've got my Cu plus 2. That means that I need 2 electrons to gain, and that's going to give me my solid copper. Again, how did I know that there was 2 here? Because my solid copper has an oxidation state of 0. This copper we know is plus 2 because we reverse crisscross. If I have a plus 2, I need a minus 2 in order to have that 0. So we had to gain to have our reduction. Now to form our complete reaction, remember my loss of electrons and my gain of electrons need to be the same. So I have a 2 and a 3. That means I need to distribute 2 electrons, everything by 2 and everything by 3 respectively for each of those. So when I write my overall, I'm going to have 2 Cr solids plus 3 Cu 2 pluses, and that's aqueous. And that's going to give me 2 Cr 3 pluses, aqueous. Oops, I forgot my AQ up here. Plus 3 Cu solids. Let's check to make sure that everything is balanced. I've got 2 chromiums, 2 chromiums, 3 coppers, 3 coppers. Good. Now let's check for charge. And I've got 3 plus 2, so I've got a plus 6 overall on the left. And I have 2 3 pluses, so a plus 6 on the right. So I'm balanced as far as charge and atoms. All right. Why don't you try to set this one up? You might not be able to do it all, but why don't you pause the video here and see if you can draw the schematic for this galvanic cell. All right, well, welcome back. Let's see what we have here. I'm just going to draw my beakers. And I'm going to, let's see, first I'm going to look at my SN4 plus and my SN2 plus. And we can see that my tin 4 plus is reducing because it's gaining electrons. So this is my GR. My zinc, Zn, so I'm going from a 0 to a plus 2. That means that I'm losing electrons. That's my oxidation. So we know that my anode on my left is my oxidation. So we know that my zinc here, I'm going to have Zn. And we know that I'm going to have some sort of solution. It doesn't tell me what my solution is, but I'm going to have zinc plus 2 ions here in solution. So I've got solid zinc. I can hook an alligator clip to my zinc metal. And I'm going to Oh, I'm going to have a voltmeter here. And I'm going to continue my wire over here. I got to have another electrode. Now notice that my other side, my cathode, where reduction is happening, we said my reduction is going from a tin 4 plus and aqueous to a tin 2 plus aqueous. So I don't have a solid. I don't have a chunk of metal for my electrode that's tin. I'm not given that. So this is where I'm going to use that inert metal like platinum, PT. Remember, that's my inert electrode to hook that alligator clip to. And the site at which this is going to happen, that site, I'm going to have my tin, my SN4 plus, turning into my SN2 plus. And these are both in aqueous form. And also to complete my circuit here, I need that salt bridge. All right, now let's see if we can write our reaction here down below. On the left, again, my anode, I've got my zinc solid. And I have my interface. And now I'm not given, it didn't say like you have 1 molar of zinc chloride or what, it didn't tell me that in just this description of our problem. So I can just be vague and I can say, oh, there's Zn plus 2, some sort of aqueous solution here. And then we have our salt bridge. And again, I can double check, is oxidation happening here? I went from a 0 to a plus 2. Yep. And then on the right side, I've got my SN plus 4, comma, SN plus 2. Both of those are aqueous. And again, I can double check. Going from a plus 4 to a plus 2 is reduction. I'm gaining electrons to do that. And I'm not told, is this tin chloride? Is it tin iodide? Is it what the solution is? We're not told, and we're not told the concentration of it. So we're just giving the vague description of the ions in solution that we were told. And then I've got my interface, and remember I use platinum, which is our inert electrode. All right, moving on. Electrodes and cell potentials. This next part, we're going to be able to describe and relate the definitions of electrodes and cell potentials, interpret electrode potentials in terms of relative oxidant and reductant strengths, and then calculate cell potentials and predict redox spontaneity using standard electrode potentials. And this is where you're going to need your standard reduction table or your standard reduction potential table. Most of the next slides have cut and pasted what we need from it, but it will help you to see where these numbers are coming from. So we're moving to quantize, to calculate cell potential. We've done a great big lecture here on how to draw electrolytic cells, voltaic cells, galvanic cells, and kind of get an idea of what it means to see those half reactions. We've been drawing these little voltmeters, and now I want to learn how to calculate what the voltmeters would say when I set up 2 half reactions and connect them, completing a circuit. When electrochemical cells permit relative redox activity, what we're doing is we're quantifying that with a measurable property known as potential, commonly called a voltage. Now, a definition of volt that we need to know. This is for future calculations as well. The term volt is defined as a joule per coulomb. One joule of energy per coulomb of charge. You can find the value of a coulomb by taking 1 mole, or Avogadro's number, of electrons, and that's where the value would come from. So again, this is the definition, joule per coulomb. In a few lessons from now, we're going to be able to use that unit to go through some dimensional analysis. On this slide, I'm really understanding what potential means. Potential between two half cells is the difference in voltage, generating a current, and that potential reflects a driving force between the reactants of our redox. We measure a difference from one side to the other side, and those two half cells call it cell potential. The E cell is the voltage of a cell. A cell consists of two halves, doesn't it? We have the cathode and the anode. So what we do is we take the cathode voltage minus the anode voltage to come up with the overall cell's voltage. So our overall cell voltage is taking the cathode minus the anode voltage to get our overall voltage. You can also think of this as reduction minus oxidation. This is a critical formula in understanding the next set of calculations. So here we've got our standard cell potential. And this is when a cell potential is measured when both half cells are under standard state conditions. Now, know these conditions. This is, if you're lucky enough to get this multiple choice question, standard state conditions is when we have 1 molar concentrations of the solutions. We're under 1 atmosphere of pressure, and it's on 25 degrees Celsius, which is equal to 298 Kelvin. These are the conditions in the lab when we generate voltage and measure it with a voltmeter. It's just called standard states. Since half reactions don't generate a voltage that you can measure, we measure potential difference. We have to have something to compare a half cell to, and that's the job of a standard hydrogen electrode. The standard hydrogen electrode that we've designed hydrogen to be the half cell as the reference for cell potential. Assigning it a 0 value, and this is called our She cell. Again, that S for standard hydrogen electrode, She cell. And now I want you to look at that table that you printed off, the standard reduction potentials at 25 degrees Celsius. And there's all of these half reactions on the left, and on the right side it says E for our voltage, and there's a whole list of them. This is a front and back side. And I want you to look at that E, the side where it go all the way down till you get to a voltage, find 0. If you find that voltage of 0 and you look over, you'll see this. This She cell, the standard hydrogen electrode, is the reduction of hydrogen and it has a voltage of 0 volts. Now let me clarify. This is what it is assigned. It's assigned 0 volts. Not to say that it doesn't have any electrical capacity. It's just we're going to call it 0 and compare every other elemental half cell to that standard. So we have to call it 0. Some things that are positive are more active at losing electrons, and things that fall below it will be less active. It's just a point of reference, assigning it as 0 voltage. So E cells is equal to the cathode minus the anode. So if you see little circles up here that represent the standard state conditions. Standard state conditions, the E cell is cathode minus anode at standard states. When we see these little circles up there, those knots, this is telling us that it is at standard state. Which means we have 1 molar concentration, 1 atmosphere pressure, 298 Kelvin. Now, we understand that hydrogen is in gaseous form. So how in the world are we going to hook an alligator clip to a gas? Well, you can't. So just as if you had ions in solution, we need an inert electrode for a gaseous reactant. So notice that this is just a vacuum tube, and it has an opening. You'll usually see this rubber hose right here, where the hydrogen gas is being pumped into that vacuum tube. And then to complete the circuit, we just put that piece of platinum wire in, and I can hook an alligator clip to that wire that's coming out of the vacuum tube. So you'll always see an inert electrode involved with gaseous hydrogen, the She electrode, simply because we can't hook an electrode to a gaseous reactant or product. So we place the platinum wire inside the chamber that contains the gas to complete the circuit. And again, this is the platinum wire, and this is the site where this is just a blown up platinum wire. It's the site where the oxidation or the reduction will occur depending on what's assigned to the other half reaction. So when we start looking at standard tables, this is the table that I've provided you as a test-taking tool. You'll probably have it printed by now, hopefully. Or if you're reading through your chemistry book online, you can click, I believe it's Appendix L, and a long list of potential differences will appear. One thing to note with this table, now if you look in some books, some appendix, I believe the one in the online text, they're listed alphabetically. This one is listed in voltage going from highest to lowest. So they're all the same. The values will be the same. This one just happens to be in order or voltage, highest to lowest, and the one in the book I believe is alphabetical. But this is also written, this is our standard reduction potentials. So these are all reduction half reactions. So you'll see the electrons are all in the reactants, regardless if we are looking at oxidation or reduction. Now, if we were trying to find oxidation values, then we simply flip this. Let's say we're looking at this fluorine. We would flip this reaction, and then we would flip the voltage value. So it's an easy flip-flop. Also worth pointing out, here we have our hydrogen She cell. We can see that that is our electron volts assigned 0. So here's our She cell. And also down here, we can see our copper reduction given a value of 0.34. And I'm going to look at that at this next page. So this picture is kind of going to help see where that 0.34 comes from when we were looking at that copper value on the page before. So on this picture, so to look back at that copper value that we were just looking at, how do we get that? Well, we've got our anode set up with the standard hydrogen electrode, which is kind of our standard that we're comparing against. And on the right, our cathode, our reduction, we're looking at copper 2 plus to copper. And when we hook that up to the voltmeter, it's going to read this 0.337 volts. So this is something that you or I could do in the lab, and we're going to get that value because we're using the standard hydrogen electrode as our comparison. So again, this is a value that compared to our hydrogen over here, something that is constant. And in this case, we have created a battery where the cathode is what we're trying to measure, which again happens to be our copper. And when I compare the activity value of the copper to the standard value cell, the voltage reads 0.337. So walking away from this, we know the cell is the standard that which we compare all other half cells to. Let's look at this example problem. Calculate the standard potential for this galvanic cell. Well, let's see what's happening here. I've got a copper anode, and we know that my anode is my oxidation. So that means if I'm oxidizing, I'm starting with my solid copper, 0. And it tells me that it's turning into my copper 2 plus ions. And if I have 2 plus ions, I need 2 electrons. So I just went from 0 to +2. Yep, it's oxidized. All right, there is my reaction happening. We know that those 2 electrons that are being released are traveling clockwise over to my silver cathode. We know this is my site of reduction. That means reduction, I'm starting with my Ag plus ions that are in aqueous. I have 1 plus, so I have 1 electron. And it's creating my Ag solid. Okay, this is my reduction. This is my oxidation on the left. Now, if you look at that standard table, I got these values just from clipping it from the table, but you could look at these values on the table and get these exact same numbers. So here I go. I've got right here my reduction. I've got my silver, and notice it looks exactly the same as what I just wrote. Ag plus an aqueous plus 1 electron to give me Ag solid silver. So here's my value, 0.7996 volts. Now for copper, if you look at that sheet and find copper, there are 3 different coppers to choose from. We want to make sure that we choose the correct one. We want copper solid. Now again, remember, these are all reduction tables, so it's going to look flip-flopped from what this tells me. So I want to start with solid copper, not copper plus, so I can cross this one off. And on the left side, remember I need copper 2 plus, not copper 1 plus. So this is the value that we want, the 0.34. All right. Now let's write down our problem here. Our E cell is equal to our E cathode minus E standard state anode. And remember, we can remember which one goes first if it's cathode minus anode, because my cell, so my whole total cell and C cathode, they're right next to each other. So those C's, cathode is minus anode. So let's take that cathode, this reduction, minus our oxidation. So my reduction is let's change color here, 0.7996 volts minus my oxidation, 0.34 volts. Now notice, do not change the sign of my oxidation value. This minus right here is doing it for us. It's flipping it. So we're not going to do a double change here to get that value. We don't want a minus a negative. This minus is flipping our oxidation value, because remember, this is a reduction value. We want oxidation. So this minus is flipping it for us. So what will my voltmeter say when I do 0.7996 minus 0.34? I'm going to get an Ecell value, and I'm limited to 2 significant figures. So my calculator will tell me 0.4596. And I'm going to go to 0.46 volts. Also noteworthy that this is a spontaneous reaction in the forward direction. And we know this because we have a positive voltage. The battery is generating a current with positive voltage. Therefore, I know just from a few chapters ago that Gibbs's free energy would be negative because it's a spontaneous reaction. So we looked up the volts Ecell found by cathode minus anode. Don't change the sign. It is not stoichiometric dependent. Do not carry coefficients into those little subtractions. Just very straightforward. Grab the number from the chart and subtract as is. Don't change a thing. Voltage is an intensive property, not stoichiometric dependent. This is another problem. So this is the same as picture as before, but we're going to replace the silver cathode with a lead. So instead of this Ag, this is going to be Pb here. And instead of Ag plus ions, we're going to have Pb 2 plus ions. Again, remember this is our cathode. Oop. And to find our Ecell standard state, we're going to do our cathode minus anode. Our cathode is our lead, and our lead has a value of negative 0.1262 volts. And our anode over here, our anode is our copper, and our copper value is 0.34 volts. So our Ecell, when we plug this into our calculator, do it with me, negative 0.1262 minus 0.34, and I got negative 0.4662 volts. And this tells me that it is non-spontaneous. So in the forward direction, this is a non-spontaneous reaction. There are no volts being able to be captured to do work. In other words, I would have to flip this whole circuit around. When we flip this and turn the cathode into the anode, take the anode and convert it to the cathode, we would get a positive voltage to make this reaction occur. It's non-spontaneous as written. The negative volts will tell me that the delta G is positive, meaning non-spontaneous. So what do we know about spontaneous reactions? We know that we have positive cell potential, so we have a positive voltage. We have negative Gibbs's free energy, so negative delta G. Also telling me that it would be exothermic or exergonic. The energy is decreasing in spontaneous solutions. I also know that the equilibrium constant for the forward reaction would favor a large number, so K is greater than 1. And then opposite of that, our non-spontaneous reactions, we would have a negative cell potential, so negative volts. Positive gives us free energy, so this would favor the reactant side. All represent non-spontaneous reactions. And then the example that we were just doing in the last slide, looking at copper and lead, and we got our negative voltage telling us that it's non-spontaneous. In order to reverse this reaction, so we can see here that our copper to copper 2 plus, this is our Leo, this is what's being oxidized, and our Pb is being reduced. So that's our GER. And because of that, having the cathode and the anode the way that they are, we get this negative voltage. But if I flip this around, so my lead going from a 0 to a 2 plus, my lead is now being oxidized. And my copper is being reduced, so that's the GER. Then my cathode and anode are reversed, and we get that positive voltage, which is telling me that it is spontaneous. Let's get this question. This was a quiz question that I just snapped. We want to know if this reaction is spontaneous in the forward direction. So let's link together here. I've got my chromium and iron and iron. We need to figure out which one's being oxidized and which one's being reduced. So I'm going chromium from 0 to +3, so that's being oxidized. And my iron, I'm going from +2 to 0. It's being reduced. All right, so then to find out my Ecell is my E cathode minus E anode. Remember, I've got my C's and C's next to each other. And my cathode is always what's being reduced. That's my because these are two consonants, C and R, and my anode is what's being oxidized. Because they're both vowels. So if I know that my chromium is being oxidized, my iron is being reduced. So let's start with my reduced. My iron, this is my Fe value because we said it was being reduced. So my Fe value I'm going to use is negative 0.447 volts minus my oxidized, which is my chromium, my Cr, and my Cr is negative 0.744 volts. Remember, write it as is. Do not flip the signs. It's not stoichiometric dependent. We're just going to plug this into our calculator to get our Ecell. And when I do this, negative 0.447 minus a negative 0.744, I got positive 0.297 volts. So yes, if it's positive, it is spontaneous in the forward direction. Let's get another quiz question. We want to look at, is the oxidation of bromide by molecular iodine under standard state conditions spontaneous in the forward direction? Well, first let's write the oxidation of bromide ion. Bromide ion is Br minus. That's going to be aqueous. Remember, oxidation is losing electrons. So over here we're going to have at least an electron that is getting rid of. But bromide to become bromine, Br is Br2, right? It's in Brinkelhoff. So Br2, that means that I have two bromines on the right. I need to have two bromides on the left to balance that out. So therefore on the left I have 2 negatives, so on the right I need 2 negatives. And notice that that looks pretty similar to down here on my reduction table. It's just flip-flopped because remember on my reduction table, those are all reductions, and this is an oxidation, so it's just flipped. So this is my oxidation, and we're given a voltage of 1.0873. So if bromine is being oxidized, that means that iodine is being reduced. So I'm going to write down my iodine, and iodine is also in Brinkelhoff. Iodine is I2, and if it's being reduced, I2 is going to become iodide, which is I negative. Well, let's balance this. I've got 2 iodines on the left, so I need 2 iodides on the right. And we know that if it's being reduced, it needs electrons. And obviously we need to balance this out. On the right side, I have 2 negatives, so I need 2 electrons on the left. And we can see down here on my reduction table, I2 plus 2 electrons, so it gives me 2 I negatives. And that value is 0.5355. That's a positive value, and this is my reduction. All right, and so going one step further, we know that the oxidation is my anode, right? Both vowels. My reduction is my cathode. And to find my Ecell is my cathode minus my anode. So let's write down these values. My cathode is my 0.5355 volts minus my anode, which was my 1.0873. If I plug that into my calculator, I get negative 0.5518 volts. So is it spontaneous in the forward direction? No. How do I know that? Because I have a negative voltage. Now, if we wanted to make it spontaneous, we would just flip this reaction around, and instead of bromine being oxidized, bromine would need to be reduced. So we would just need to flip, so everything on my right side would need to be on the left. So we would have Br2 plus 2I minus. Again, remember in our final equation, we leave our electrons off, and they're 2 and 2, so perfect, to give us 2Br minus plus I2. This would be spontaneous. And instead of bromine being oxidized, we would need bromine to be reduced, and it would be the cathode at that point. And instead of iodine being reduced, it would be oxidized, and then it would be at the anode. And by doing that, my voltage, since I'm flipping the cathode and the anode, I would have a voltage of positive 0.5518 volts, and that would give me a spontaneous forward reaction. We're going to kind of bring together in our final closing here the potential free energy and equilibrium relationships. Our goal is to explain that the relations between potential free energy change and equilibrium constants, tying these all together, we will perform calculations involving the relations between cell potentials, free energy, and equilibrium. So we'll think about the voltage, the Ecell, free energy, Gibbs us free energy, and equilibrium constant K. The potentials, the free energy changes, and the equilibrium. And it's actually not until the next video lesson, but the Nernst equation will help us to determine the cell potentials under non-standard conditions. So when I say Ecell is equal to the cathode minus the anode, you see that those super knots, those zeros, the E naught for these represent at standard state conditions. But what if we're not at standard states? I need to show you an equation to calculate for non-standard conditions. But first, let's focus on free energy, voltage of E cells, and the equilibrium constant. We know that standard free energy, called Gibbs's free energy, was defined as the maximum work that could be performed by a system. And I know that work for redox reactions is associated with the transfer of electrons from reactants, from what's being reduced to what's being oxidized. A transfer of electrons. And what I really need to know and walk away with here is that redox reactions are defined as the transfer of electrons. That's work being done through an electrical circuit. Work associated with the transfer of electrons from the reactant to the oxidant. The work associated with transferring electrons is determined by the total amount of charge transferred and the cell potential. So this is an important equation to know. We have Gibbs's free energy. It can be found by setting equal negative N times F times E cell. And here we're given N. N is the number of moles of electrons being transferred. F is Faraday's constant. And then our E cell is our standard cell potential. So how do I find N? Well, let's say that I have Fe plus 2 plus Cu, creating Cu plus 2 plus Fe. So I've got a reduction and oxidation happening. So let's see what I've got here. A total charge on the left is plus 2. Total charge on the right is plus 2. So I have 2 moles of electrons being transferred. Here's another example. If I had 3 magnesiums plus 2 aluminum plus 3 ions, converting to 3 magnesium, 2 plus ions, and 2 aluminums. Okay, so if I look at total charge on the left, I have 2 aluminums that are plus 3, so plus 6. And total 3 magnesium plus 2s, so plus 6. So my N for this would be 6. So 6 moles of electrons were transferred in that redox reaction. 6 is the net charge from the balanced equation that allows me to find the N, the number of moles of electrons being calculated. F in our equation, Faraday's constant, is given to you. You don't have to memorize it. I have it on your equation page, your cheat sheet. 96,485 coulombs per mole. And of course, E cell is the standard cell potential, the cathode minus the anode. So here's some formulas to know. And you're given all of these on your cheat sheet, but I just kind of want to go over these, especially this pyramid that lets you go from equilibrium constants to G, Gibbs's free energy, to E cell voltage. And just a few things to note when we're using these, get into Gibbs's free energy, negative RT, natural log of K. Again, make sure that you remember that R is our gas laws constant, which is 8.31, and the units are joules per Kelvin mole. And you need to make sure that for finding Gibbs's free energy, if it's in kilojoules, then we need to use our R constant. Instead of in joules, we need to convert it to kilojoules, just 0.00831 kilojoules per mole Kelvin. And make sure that your temperature is in Kelvin. Over here for your Ecell, this is a voltage unit. And we learned just a few slides ago that voltage is equal to joules per coulomb. So for our R, we want to use that 8.31 joules because that's what we want for our top number here. We don't want to use the kilojoule. Joules per Kelvin mole. Again, temperature is going to be in Kelvin. Our N is our moles that we just were talking about. Faraday's constant, that will give us the coulombs that we need. And then, of course, the natural log of K. And then down here, to go from Ecell to G, or G to Ecell, we've got delta G is equal to, again, negative NF, and then Ecell at standard state. And we know that N is our number of moles, F is our Faraday's constant, and our Ecell at standard state, our cathode minus our anode. So take a little bit, again, you're giving these, but it will help to go through them so that it's easier to recognize and get from one unit to another. This chart just kind of ties it all together. If I have a K of greater than 1, that means that we're favoring my products. And with a delta G of less than 0, that's telling me that it's a negative number, less than 0, so that's a spontaneous. And an Ecell greater than 0, so a positive voltage, also spontaneous. So these reactions will be spontaneous under standard conditions, and those products are more abundant at equilibrium. Now, if we look at that equilibrium and it's less than 1, that means that we're favoring the reactants. A delta G of greater than 0, so a positive delta G, non-spontaneous. And that's the same Ecell, a voltage less than 0, so a negative voltage. It's telling us those reactions are non-spontaneous in the forward direction under standard states, and those reactants are more abundant. And then K at 0 is telling me that we're at equilibrium. And that reactants and products are equally abundant. Let's look at some example problems. Using the data from Appendix L, all that's saying is using your standard reduction potentials chart. Now, these two down here have just been, I just cut and pasted them there. On a quiz or a test, you're going to need to use your standard reduction chart to get these values. So we want to find the standard cell potential, the standard free energy change, and the equilibrium constant. So we're going to go back and use that triangle going from K to G to Ecell. We're going to be using these equations. All right, so let's see what we have here. We have AG plus going to AG with a 0. So we're going from a +1 to a 0. That means we're becoming more negative. That's our GER. That's our reduction. And here we have Fe to Fe2 plus. So I have 0 to +2. It's being oxidized. All right? So remember, my reduction is my cathode. My silver, right? Reduction is cathode. Both consonants. My reduction we just said was silver. So this is my cathode. Down here would be my anode. So when I'm finding my E cell, it's my E cathode, minus E anode. So I'm going to do 0.7996 volts minus a negative 0.447 volts. Let's plug this into our calculator, and I get 1.2466. And because this is a positive value, that tells me that we are spontaneous in the forward direction. Okay, that also gives me a little heads up that I should have a delta G value that's negative, and I should have a K value that's greater than 1. If I look back here, we just said that my Ecell was positive, so it's spontaneous. That also means I should have a negative delta G and a positive K. That'll just kind of help us as we go through this next few problems here. So now let's find G. I'm going to go back and to find G knowing Ecell. So we just found Ecell. Now let's go and find G. We're going to use this equation. Delta G is equal to negative NF Ecell. All right, so let's look at, I'm going to highlight up here. On the left, I have two Ag pluses, so I have a 2 plus on the left, and let's double check on the right. I have one Fe2 plus, so we have 2 moles of electrons. So when I write in my delta G down here, delta G is equal to negative 2 times F. Faraday's constant, we were given on the page before, is 96,485. And this is 2 moles, sorry, 2 moles. 285, this is coulombs per mole. And then we're going to times it by our Ecell that we just found, 1.2466 volts. All right, let's plug that into our calculator here. Okay, so when we plug this all into our calculator, we're going to get negative 24055.6.4. And let's see what we get, what we cancel out here. Moles and moles cancels out. And remember, volts is also, the unit is joules per coulomb. So if I were to substitute that in there, coulomb and coulomb will cancel. So we're just going to be left with joules. Now remember, we want our delta G in kilojoules. So I'm just going to move my decimal point back 3 spots. So that'll give me negative 240.6. There we go. And this will be in kilojoules or kilojoules per mole, either one. All right, so this is our delta G. All right, you're looking good. And look, we have a negative delta G, which we said we needed in order to be spontaneous in the forward direction. And then finally, we just need to find K, the equilibrium constant. And to do that, I'm going to flip back to this triangle up here. We just found G, and we know Ecell too. We could go either way. We could use either one of these equations. I'm just going to go here and use our delta G is equal to negative RT ln of K. Negative RT natural log of K. So this is what we're going to be finding. So I'm going to plug in what I just found for G, that negative 240.6 kilojoules is equal to negative R. And we're going to be using our kilojoule R because we know that R can be 8.31 joules per Kelvin mole. But because my delta G is in kilojoules, I'm going to use the 0.00831 kilojoules per Kelvin mole. So negative 0.00831 kilojoules per Kelvin mole. Our temperature, again, we're at a standard state, so 298 Kelvin. And then natural log of K. So I'm going to do a little simplifying here. I'm going to simplify these and divide both sides by that answer. So negative 240.6 divided by what I get when I multiply the right side together. I should get 97.16 is equal to the natural log of K. And then remember the opposite of natural log is Euler's number. So we're going to do E raised to the 97.16 to get K. And it should be a very large number. Remember, looking back here, for it to be spontaneous, we need K to be greater than 1. So I should get, so second function, that's the natural log of 97.16, and oh yes, it's a big number. I got 1.57 times 10 to the 42nd for our equilibrium constant. So we have found K, the equilibrium constant. We found delta G, Gibbs's free energy, all from knowing the standard voltage of your battery, the Ecell. Once we know the standard voltage of a battery, we can find our formulas to find out Gibbs's free energy, and we can find equilibrium constants from those relationships. That's really the big practice, trying to go from one unit to the other with your equations. All right, this is the last example. I know this has been a really long lesson. I want to give you a second to think about. This is just set up like the other problem. What is the standard free energy change and the equilibrium constant? And I want to know Ecell for the following reaction at room temperature. Is it spontaneous? So take a second, figure out what's being oxidized, what's being reduced. How do I figure out that cathode and anode? See if you can get from one unit to the other and then check back. Okay, let's look at this. I've got tin going from 0 to +2. It's being oxidized. And then I have copper going from +2 to +1. It's being reduced. All right. Then, if I know that my tin is being oxidized, so Sn, if it's being oxidized, that means that it's my anode. My copper being reduced, that's my cathode. So to find my Ecell, I'm going to do cathode minus anode. So 0.153 minus my anode, negative 0.1375. So Ecell should be positive 0.2905 volts. That tells me it is spontaneous. That also tells me that I should have a negative delta G and a K that's greater than 1. All right, let's go and find delta G next. I'm going to draw a little line here. Delta G is equal to negative NF Ecell. Okay, let's find what that N is. So I'm going to look at my left side, and I have two pluses. That means on the left I've got +4. Okay, so this one is going to throw us for a little bit of a loop. It is important that we check the oxidation and the reduction, and we actually double check to see how many moles of electrons were transferred. Yes, the charge is +4 on both sides. That's good, that matches, but Let's look through at this oxidation reduction. So I've got my tin, solid tin, and it is going to SN2 plus. All right, that's my oxidation. So that means on my right side, I need 2 electrons. Okay, and then that's my oxidation. My reduction is my copper, my Cu2 plus, and it's converting to Cu plus. All right, so to get my 2 plus down to plus, I need 1 electron. That would get both of those to +1. Now we know that Leo needs to equal Ger. So because I have 2 electrons on the right, I need 2 electrons on the left. So everything here needs to be multiplied by 2. All right, so therefore our N is equal to 2. 2 moles of electrons are being transferred. All right, so when we plug this in, we're going to have delta G is equal to -2 moles times Faraday's constant, which is 96,485 coulombs per mole. And then times that by our Ecell, which we just found was 0.2905. And volts, I'm going to plug in our other unit for volts. 1 volt is equal to 1 joule per coulomb. Just so we can see those units cancel, coulombs, coulombs, moles, moles, and we're left with joules. That should give us -56,057.785 joules, and I want my delta G in kilojoules, so we're going to just say -56.1 kilojoules. That's good. That's a very negative number. That's what we want. Okay, last step. Let's get to K. We're going to plug in our delta G is equal to -RT, natural log of K. We're going to plug in the G we just found, the -56.1 kilojoules is equal to -R. We need the R in kilojoules, so 0.00831 kilojoules per mole Kelvin. Our temperature, standard temperature, 298 Kelvin, and then natural log of K. So let's divide both sides by whatever this product is, and we should get natural, and then we're going to take e to the answer that we get there, which will be equal to K. And so K should be equal to 6.9 times 10 to the 9th, which is a very large equilibrium constant, telling us that it favors the product side enormously. Oh my goodness. So this was a super long lesson. You did fantastic. We found the equilibrium constant. We found Gibbs's free energy. We found our Ecell, which was positive. This telling me is spontaneous. This was telling me product favored. And you did awesome. I celebrate you, commend you for sticking through this. And I will see you for the next lesson on Nernst.